Hi, in this video I'm going to discuss Friedel-Crafts alkylation, which is another type of electrophilic aromatic substitution. So in a Friedel-Crafts reaction, in this case a Friedel-Crafts alkylation, the benzene ring again acts as a nucleophile, but this time the electrophile is going to be a carbon. In the last video we had a nitro group as an electrophile, SO3 group, bromide as the electrophile. This time it's a carbon. So this is a great reaction because we're able to make a new carbon-carbon bond, which is not super easy to do in organic chemistry. So this gives us a great way to make that new carbon-carbon bond right there. So what's the mechanism of this Friedel-Crafts alkylation? So the first step is forming our electrophile. So I'll do that in orange here. So we have this alkyl chloride. We react it with the Lewis acid aluminum trichloride. So that reacts with the aluminum. So now I formed this complex here. Positive formal charge on the chloride, negative formal charge on the aluminum. The chloride then leaves, and I'm left with my electrophile. So now that I have that electrophile, my benzene ring, one of the pi bonds from it, will react with the electrophile to give me that, right? So similar to the other electrophilic aromatic substitutions, we have the carbocation on the ring now, right? This is in resonance. With that, and now to reform my catalyst, my chloride will react with the hydrogen, and then the electrons from the carbon-hydrogen bond return to the ring. And I have my final product of the reaction. So great way here to form a new carbon-to-carbon bond. Now this example I used a alkyl halide that gave me a secondary carbocation. So right, this mechanism that I just did works for secondary and tertiary alkyl halides, because in this case I form either a secondary or tertiary carbocation, which is stable enough. Two notes. One, be careful of either a methyl or hydride shift. Right, so say I form my say I do this and I form my carbocation. I have to be careful, or I guess say I have this. I have to be careful that I don't get a methyl shift and end up getting that. The methyl shift would happen because now I can have a tertiary carbocation instead of a secondary one, which is more stable. So you have to be careful that the substrate you're using with the alkyl chloride isn't able to undergo either this methyl or this hydride shift. Number 2 is that we cannot have a primary carbocation but a complex will form instead. So we'll get a complex instead of a primary carbocation because that is not stable. But say I have this as my alkyl chloride. What will happen is when I react it with aluminum trichloride, I'll get this complex. And rather than this leave, instead, the benzene ring will react in almost an SN2 fashion. It'll come in and kick off the complex. And then I'll get that. Right, so you can still have the Friedel-Crafts alkylation occur with only a primary alkyl halide because you form this complex which does not leave, and instead you have an SN2 type mechanism to add on the electrophile. A couple more notes. The carbon bonded to the halide must be sp3. Right, if I had either of these two substrates, so if I had that or say I had another, benzene ring with a chloride on it, you would have no reaction for Friedel-Crafts. Right, you have to have an sp3 hybridized carbon. Another note, and I'll talk about this more in a couple videos with activating and deactivating groups, but often installing one alkyl group makes the ring more reactive. So this means I'll have polyalkylation. To only install one group onto the ring, I have to be very careful with the amount of reactant I have, because if the ring becomes more reactive once I install a group, it'll pretty easily add another alkyl group onto the ring, so I have to be careful about that. So my next video will be on Friedel-Crafts acylation, which is a similar mechanism with just a slightly different reactant.